This video will discuss perhaps Einstein's most famous equation to the public, at least, E equals mc squared, and the relationship between mass and energy. In 1905, Einstein had a very productive year of publishing papers with special relativity, the photoelectric effect, and came to the conclusion that there was a relationship between mass and energy. So E equals mc squared. E is the energy measured in joules in standard metric units. M is the mass in kilograms. And c is the speed of light. It has a value 3 times 10 to the 8th meters per second. This is 300 million meters per second, again in standard metric units. So one way of producing electricity for consumption in homes might be a nuclear power plant. It turns out when uranium fissions into smaller nuclei, we get a release of energy. In the sun, in the center of the sun and other stars that are newly became stars, at least, we have the principal nuclear reaction of hydrogen fusing together to form helium. In both of these situations, the mass before the fission or fusion takes place is greater than the mass after the fission or the fusion. And this missing mass, this mass difference, becomes energy. To turn a turbine, boil water, make steam, and turn a turbine, or to create the temperature and pressure in this inside of the sun that supports the outer layers, the great weight that's pressing down. So we want to talk about, for some hypothetical city, it has 200,000 homes. Each home uses 11,000 kilowatt hours in a year. What type of unit is the kilowatt hour? Well, the watt, that's a standard metric unit. It's a joule per second for 1 watt. When we multiply by another time unit, the hour, we don't get direct cancellation of hours and seconds, of course, but this is an energy unit. The kilowatt hour is a measure of energy. And we want to know what mass would match this energy use. 200,000 homes, and each home using 11,000 kilowatt hours. So I'm going to put several factors here and multiply them out. So we'd have the number of homes in scientific notation. 1, 2, 3, 4, 5. I have to move 5 places. So I'm going to do 2 times 10 to the 5th homes. Each home is using 11,000 kilowatt hours. So I'm going to represent that as 11 times 10 to the 3rd. And I'm going to go ahead and write kilowatt and times hours. This is per home. So we've canceled off the homes unit. And now let's deal with the kilowatt. There are 10 to the 3rd watts in a kilowatt. So we cancel off the kilowatt. And then what about the number of hours? How do we change that? Well, the watt is a joule per second. I'm just going to write that up here, joule per second. So we need, instead of 1 hour, we need the number of seconds in an hour. So that's going to be 3,600 seconds in 1 hour. And we'll be using the seconds to cancel the seconds that are part of the watt unit. The watt is joules per second. When we multiply by seconds now, we'll be just left with joules. We'll be left with joules. And you should repeat this calculation on your own calculator. Make sure I did it correctly. I came up with 7.92 times 10 to the 15th, and probably should round it to 8 times 10 to the 15th, since hypothetical round number of homes in the city, hypothetical average energy used for a year. But let's go ahead and use this, and then we want to find what mass does that relate to. If this is nuclear power operation, what mass has to, I won't quite say disappear, but what mass has to become energy for supplying energy to this city. So we have the number for the energy, 7.92 times 10 to the 15th equals the mass, and then 3 times 10 to the 8th, and that has to be squared. Again, you should work this out in your calculator. If you're not familiar with powers of 10 notation, do a search for my video, Powers of 10, put Clements in the search, and you'll see some examples of power of 10 calculation. But 7.92 times 10 to the 5th divided by, this is going to be 9 times 10 to the 16th when it's squared. So we do that division, and we find that we get 0.088 kilograms is the value for M, 0.88 kilograms. If I want to talk about grams, this is kilogram. I'd have to shift by 3 places. So this would be about 88 grams. 88 grams of mass is equivalent to the amount of energy to supply a city of 200,000 homes that each use this average amount of energy per year. So that's, you may or may not think that's a lot. It's not really very much. 88 grams disappearing. Just very, very roughly. So the uranium doesn't disappear. But a small fraction of the mass of the uranium changes into energy, and then we get other smaller elements, smaller nuclei, as a result of the fission process, but most of the mass remains. This conversion here, this nuclear process, and using uranium as a fuel, very, very roughly, power plants, nuclear power plants, the weight of the fuel is about 1,000,000 times less than the weight of coal that would supply the same amount of electricity. So very, very roughly, nuclear reactions are about 1,000,000 times more energetic than chemical reactions, the burning of coal. So nuclear power plants don't need a lot of fuel. And that's probably a good thing because uranium is not really common. It's a little bit rare. Coal is much more abundant. But the nuclear power plants, I won't get into all the pollution savings that they have. There are also dangers of radioactivity. My first teaching job was in Carlisle, Pennsylvania. In my first year of teaching in the spring was the accident at 3 Mile Island. And our college closed for a week during that uncertainty around that accident. So if you have questions on E equals mc squared, be sure to ask your instructor. In this calculation, the energy must be in joules, the mass must be in kilograms, the speed of light very, very close, 3 times 10 to the 8th meters per second.